Welcome to the course on power quality. So, we are going to discuss modeling, simulation and performance of hybrid power filter. Well, this is the first case study related to modeling, simulation and performance of passive series and passive shunt based hybrid filter. So, we are using here passive series filter as well as passive shunt filter for mitigating the harmonics of this nonlinear load, which is shown here 25 kilowatt nonlinear load. And well, after proper designing of these two passive filter, we have the data of here the typically of passive shunt filter data. I mean typically passive series filter data, I mean like a kind of the parameters which are shown C5, C7 and CH here, and then the L5, L7 and LHF typically here. And similarly for passive shunt filter, here the data is given here. In passive shunt filter, we are using only one filter, and that is typically high pass kind of filter, and series of course, we are using a band pass filter of 5th order, 7th order and high pass like. So, properly designing this, of course, we discussed already earlier that in this case of this hybrid filter, there is a drawback of passive series filter, that at fundamental frequency it behave as a inductive reactance or as a inductance. So, it certainly this inductance causes the voltage drop, but passive shunt filter, I mean at fundamental frequency it behave as capacitive. So, this gives the reactive power to maintain the voltage at the point of common coupling. And moreover, this series filter certainly blocks the harmonics, because high pass all the high order of harmonics, and C5, 7 these two filters block the 5th and 7th lowest harmonic. So, because of this, even the resonance with the supply system is also not there. So, both the drawback I mean of series filter is taken care by shunt filter, and the drawback of shunt filter is taken care by series filter. And after proper designing of this filter, I mean we are able to get typically a quite good performance. So, for the simulation study, the supply voltage considered for 1550 hertz and voltage fed nonlinear load with load power of 25 kilowatt is considered for simulation study, and the reactive power of passive shunt filter design is considered approximately only 15% of active power, because this kind of load does not need much reactive power. Only for the source impedance we need some kind of reactive power, and the various filter parameters are given in the table which we have already seen. And the response of the series passive filter and shunt passive hybrid filter configuration for study is shown in next figure, and only with the series filter and only with the hybrid filter. So, you can see the typically here your response here, these are supply voltage, and you can see the supply current, I mean like here, and of course, this is the voltage at the point of common coupling of the diode rectifier input, and this is the typically you can call it the load current, I mean like. So, if we are putting only, let us say you are just keeping, like if we are putting only series filter, we are getting some performance, but after switching on the shunt filter, we are able to get improved performance further in the supply current. That will just of course, we will see the harmonic analysis, but you can clearly see now the load current, I mean like are certainly much different with the shunt filter compared to series, but supply current are sinusoidal. So, you can see here the supply current TAD, I mean order of 2.97%, and typically with alone passive series filter it was 5.33, you can see this, but after putting hybrid filter it is reduced to 2.97. So, this reduction of half by putting shunt filter is reduces to typically only 2.97, because the standard says of 5%. So, we are able to reduce less than 5% by using a combination of both the filter like or so. So, that is with the hybrid filter which is lower, and with the passive series filter only it is 5.3, but certainly it blocks large number of harmonics, which otherwise the normally teaching total harmonic distortion such kind of load without filter is around 60 to 65%, which reduced to 5.33% only by series filter, but if we put shunt then it further reduces 2.97% like or so. Well, and the voltage certainly at the point of voltage of the source is also improved, because now we are not drawing the harmonics current from the supply, so it reduces even much lesser than 1% or of that like also. And however, the voltage at the PCC at the input of diode rectifier it is 19.69. This is only possible when you really able to force the conduction of all three phases, then only you are able to probably, and in diode rectifier if you are forcing all the three phases to conduct, at the input the voltage is bound to be of this shape only, then only you will be able to get the typically conduction of all the three phases, and you will be able to reduce the harmonics current in the supply system like also. So, that is about supply voltage and load voltage. and then this is typically you can call it the load current. I mean load current are, I mean we are not distorting too much, I mean because in such kind of configuration you can have a voltage fed or current fed load, but the load is not disturbed in that case like also. So, now this is the another configuration which where what we are talking about, that we are using passive shunt filter. I mean you can understand why this earlier configuration of passive, because the all passive element if we put it become quite bulky, I mean like and lossy also, but normally passive shunt filter are used in practice. But the problem of this passive shunt filter is related to the resonance and fixed compensation. But if we put a like a small series active filter which may be hardly a rating of 4 to 5%, not more than that, then this series active filter is able to make this as an adjustable solution and avoid the resonance. Because now in this filter we cannot have a harmonics which can be very high amplified, which probably may be because of the source impedance resonance with the this nonlinear load like. So, that it blocks the resonance. Apart from that, it makes this passive filter effective as adjustable solution in the sense that you can inject the different amount of your harmonic voltage, so that the different amount of harmonics current flows into passive filter and the supply current are completely relieved from the harmonics. So, you can call it like a lone passive filter have been the, you can call it like a relative compensation. I mean you can reduce because, but there should be some harmonic voltage. I mean suppose series filter is not there, so there should be some harmonic voltage, then only this passive filter will draw the current because it is a passive network. But if you are putting a some series, I mean active filter here, you can generate the voltage harmonic and push the current into passive filter of variable magnitude, how much as the load current draws the harmonics like. So, certainly in that case, I mean the typically your current in harmonics in the supply can be reduced to quite low value, and sometime of course, control of the series active filter, I mean which is connected in series with passive shunt filter is also we control indirectly these current. So, if we are able to force these current to be sinusoidal and balanced, then it means we are able to force all the harmonics to flow into this indirectly. It means we are generating some harmonic voltage in series with the passive filter like. And with this proper, I mean design and with the proper control, we are able to get the performance with these. These are the data of passive shunt filter and active series filter, I mean typically, and we can look into a performance quite good in a sense that you can say supply voltage and supply current, I mean like, as well as you can call it the I mean they are balanced sinusoidal in phase with the supply voltage. And of course, these are typically the load current which we are not disturbing here, and these are the shunt filter current also, and this is the voltage across the series filter, I mean which is you can see not much higher or so, and this is the DC link voltage of the series filter. So, you can call it like a very small rating of typically of this your active series filter, you are able to I mean improve the performance of this passive shunt filter also. And you can see now the TAD of supply current is hardly reduced to 1.52%. Otherwise, if this filter is not used in voltage fed kind of load, the total harmonic distortion is normally between 60 to 65%, which reduces to less than 1.52%. And since this is quite effective for even for the developing country, because the power electronics converter is used very small rating of hardly 4 to 5%, where the 95% or 98% burden goes to the passive filter, which can be certainly manufactured locally even in the developing country like India or so. And this is the typically the load current TAD, I mean which you can see clearly that we are not disturbing the load. I mean load TAD is quite high, but the grid current TAD. So, it means all these harmonics which are here dominant, we are able to force into the passive filter like, I mean, and typically, and you can see the voltage, I mean TAD is also not very high, like around 2.7%. It hardly, it also depends on source impedance how it is really. So, it becomes quite effective this topology and practically used in practice. This is another topology which is very much preferred, especially for current fed the load. So, we normally current fed the load, we keep a passive shunt filter because we should not change the behavior or disturb the behavior of the load. Behavior in the load in the sense these currents should be Cauchy square wave in case of 3 phase, because you have a load might be drawing the constant DC current. So, when you have a constant DC current, this current becomes a Cauchy square wave for 3 phase thyristor converter of this kind of the load, and we have a passive shunt filter. So, we are bound to, I mean if it needs some reactive power, this reactive power we will be able to give from passive filter. Passive filter design we can keep so that whatever the reactive power this load nonlinear load of current fed type needs, it should be able to provide locally, and whatever the harmonics current under varying load condition it needs, we should be able to force that much harmonics current into passive filter. How will be able to do it? Because we inject a suitable voltage in series with the line at the point of common coupling, that voltage may be a variable voltage which will force the variable current into passive filter, and moreover once you have a series active filter, it will block the even the resonance problems also. So, it avoids the resonance problem, and it make this passive filter adjustable solution for such kind of load. And the rating of this active series filter is hardly again 3 to 4%. So, if it is a rating of 4% of active series filter able to make an entire burden goes to 96% to shunt filter, the cost of this hybrid filter can be quite low, and that is the reason it is acceptable into practice like or so, because you are using a power electronics hardly 4 to 5% rating of the load rating also. So, this topologies have been also quite popular, either whether it is a typical current fed load or voltage fed kind of load with this hybrid combination like. And this is typically the design of course, the passive filter for this current fed the load, and you can understand why the base 4 capacitor is decided, that is reactive power of the load, and the inductor is decided corresponding to, you can call it like a quality factor, and tuning corresponding to that particular frequency, that is L, and R decided by quality factor. And of course, this is the series filter, only the ripple filter is required in that case, and DC link voltage and interfacing inductance like also. Well, so after completely designing and typically simulating the behavior for 25 kilowatt, this voltage typically current fed kind of the load. Current fed load in the sense load current is quasi square here, you can clearly see here, and you can clearly see the voltage of quite good sinusoidal and supply side, and this is the typically the current, you can call it in the supply, which of course with the proper design of passive filter, it is there at unity power factor, harmonics are also less and no reactive power burden on the supply system, and this is of course the voltage at the typically you can call it across the load, and this is the load current which is not disturbed like, and this is the passive shunt current, passive filter shunt filter current, and this is a small series active filter voltage. You can see very small voltage we are injecting in series with the line and forcing virtually the entire current into the passive shunt filter, whatever the harmonics are generated by this load like, and this is of course the DC link voltage for providing the self supporting DC bus. And after like you can see the performance that the TAD of typically of the grid current is reduced to 1.4%, and where the typically the TAD of voltage is PCC voltage is also 0.33%. Why it is reduced? Even the voltage TAD also reduces, because now we are not even flowing the much harmonics current into the source impedance, because that is only a small harmonics are flowing in source impedance. That is the reason voltage are also not distorted, in spite of you might have a reasonable amount of typically the source impedance like also. And then typically you can see the load current TAD around 21% like a quasi square wave. So, we are not disturbing the load, like current fed load needs the constant current on DC side, and this will give the constant current on the DC side, whether it is the load is your current source inverter fed synchronous motor drive or induction motor drive, or your any other drive, permanent brush, permanent synchronous motor drive. All these cases this kind of, or DC drive, or you are driving a current source for feeding those current source inverter similar to like HVDC or many such applications. So, we are not disturbing the load, still the current remain constant on DC side, and we are able to improve the power quality on the grid side by maintaining the harmonics also less than even 5%, as well as the reactive power almost to negligible on supply side by properly designing the passive filter in that case like. So, this is another, you can call it like a case study where we are using two active shunt filter, shunt active filter and series active filter. This is similar to what we discussed already of UPQC, but you can understand the difference in UPQC and here this hybrid filter, active hybrid filter is that we assume that you have a harmonics in the load, current harmonics and voltage harmonics in the supply voltage. So, this load needs really a good quality voltage at the point of common coupling, so that load is not disturbed, as well as you probably will have a sinusoidal supply current. So, this will be able to give both the good quality in this case like also with this, and the DC link voltage regulation or control is responsibility of shunt active filter, as we were doing earlier too. But whatever the active power this series filter needs, either it takes the power, active power it releases or it accepts it. It is by maintaining the DC link voltage, shunt filter have to provide like similar to like a UPQC or so. And after designing this, these are the interfacing inductor for both and the ripple filter capacitors, like in both cases, and this is the performance. So, you can see the grid voltage is quite distorted, but you can call it the load voltage is quite sinusoidal and grid current is also sinusoidal like. And this is typically the load current. In voltage fed kind of load, you get this kind of the current with a couple of notches with quite good harmonics, and this is of course DC link voltage and typically the shunt filter current and the series voltage injection like. So, you are not injecting much large, you can clearly see very small voltage are injected in series with the help of transformer of series active filter. But this solution certainly have a very interesting part, because you can have adjustable solution, in the sense you can generate adjustable amount of harmonics either by series or shunt or by combination of both. So, it is not like a passive, I mean passive filters that which have a fixed compensation. Here you can have adjustable current by, I mean your, because you are using voltage source converter for shunt as well as series filter, like I mean also. And you can see clearly the load THD, I mean is around 80.53%, I mean like also, and the grid current THD is reduced to 2.18%. Just see the difference, how much reduction is has gone to really in the grid current from your load voltage. And you can clearly see the peak current of the supply is also reduced compared to the, you can see the peak of the load current. The peak load current is probably around, let us say maybe around more than 80 ampere, is stretching almost 100 ampere, but the peak of your source current is hardly around 50 ampere. So, it means whatever you can call it like a high order harmonics and high crest factor also reduce, I mean typically here by like 80 to order of 50, like I mean. So, that makes a big difference, that the peaky current is also avoided, not only the harmonics current, especially in case of voltage fed kind of the load like. And then you can see the voltage, I mean typically where the source voltage was having quite good large harmonic distortion. It may be distortion either from supply side, or it may be distortion because of the other connected load at the point of common coupling. You may be getting quite distorted voltage of this nature at the point of common coupling, but still your load is not affected, because your load is getting good quality of voltage of less than even 1.47% THD across your load. So, the series active filter is able to clean your voltage from this voltage to this voltage with a quite low THD, again from 22.35% to hardly about 1.47% only, and current THD is certainly reduced to drastically, you can call it like 80% to 2.18%. So, it causes a drastic improvement in current profile as well as the voltage profile, current profile of the grid and voltage profile across the load by using this universal active filter, which is a combination of series active filter and shunt active filter, like I mean with the common DC bus here with proper control like also. So, these are the some of the case study. Now, we will discuss some of the numerical examples. So, coming to the first numerical example, a single phase voltage source inverter with a square wave AC output of 230 volt 50 hertz is feeding the critical load of 230 volt 50 hertz single phase 5 kVA at 0.85 lagging power factor, and single phase universal active power filter conditioner UPAC consisting of shunt and series active power filter using 2 VSC with common DC bus capacitor is designed for this critical linear load. Calculate the voltage rating of shunt element of UPAC, universal active power filter, current rating of the shunt element of universal active power filter, voltage rating of the VA rating of the shunt element, and voltage rating of series element, and current rating of series element, and the VA rating of series element of universal active power filter to provide the load compensation for unity power factor at 80 means and by shunt element, and constant regulated sine voltage of a 230 volt RMS 50 hertz across the load by series element of UPSC. So, you can see that this inverter is, I mean giving you like a square wave voltage, normally I mean the kind of like a might be a domestic inverter or otherwise, and we want across the typically the load a sine voltage, across the load here sine voltage. So, the difference of these two, we have to inject the voltage, that is the series injected voltage here. So, this voltage is a sine wave, and now you can say the typically here, I mean because it says like a series filter here. So, current in the, you can call it, this is a shunt filter current which takes only reactive power of the load. So, you can call it the load, I mean your load current, I mean typically the load voltage is sine wave, and even this you can call it your load current, I mean here it is having lagging power factor which is given by shunt filter, and you have a supply current in phase with the supply voltage at unity power factor. So, this universal active filter is able to eliminate the harmonics from the input voltage, so that load voltage is sinusoidal. It also provides the reactive power and harmonics, of course, here reactive power for the load, so that the supply current is in phase with the supply voltage and power factor unity, I mean displacement factor is unity on the supply side like also. So, coming to numerical part of this, given that a Vs equal to 230 volt RMS square wave, F is equal to 50 hertz, a critical load of 230 volt 50 hertz single phase 5 kVA 0.85 lagging power factor, and fundamental component of supply voltage for square wave voltage is estimated at Vs1 equal to 0.9 Vs, and that is 0.9 230 equal to 207 volt, and the load voltage is to be regulated at nominal sine voltage. Hence, the load voltage is 230 volt, and the AC load current is as IL equal to SL upon VL. So, it is a 5000 by 230. So, this is the load current 21.7739, and in this system load reactive power compensation is to provided by the shunt active filter of universal active power filter, and the voltage compensation provided by series active filter. However, there is a difference in magnitude of the fundamental voltage in the supply and load terminal. To compensate that, an active power is circulated between series and shunt active filter. As explained earlier in UPVC, the rating calculation of both of VSC of universal active power filter are as follows. So, we know the load active power, we know the apparent power of the load and power factor. So, this is the your let us say apparent power factor multiplied. So, this is 4250 watt is the active power drawn by the load, and active power component of the load current is estimated as PL upon divided by VL. So, this comes like 18.478 ampere, and the supply current after the compensation of course will be corresponding to, because the you can call it the voltage at the supply side, I mean only your fundamental voltage 207. So, you will find the fundamental current of order of 20.531 ampere, and the voltage rating of the shunt element of U is equal to the load voltage 230 volt, since it is connected in across the load of the 230 volt sine wave waveform. So, current rating of shunt element is computed as the shunt element of the universal active power filter is to correct the power factor of the load to unity. Hence, it supplies the reactive power required by the load. Therefore, reactive power requirement of the shunt active power filter is estimated as your ISHR equal to reactive power component of load current, and that is IL under root 1 minus power factor square. So, if you put the value, then it comes 11.453 ampere, and the supply fundamental voltage lower compared to the required load voltage. Hence, the shunt active filter absorbs the active power, and that active power is delivered back to the system via series active filter. So, active power component of shunt active filter is estimated as you can call it the difference of the, you can call supply current minus this load fundamental current, and that much is the active component of current which is really flowing into the shunt filter, and the net current rating of the shunt active filter is the active component square plus reactive component square under root of that. Putting the value, it comes 11.635 ampere, and the VA rating of the voltage source converter is a voltage rating multiplied the current, it comes 2675.956 volt ampere, and the voltage rating of series active filter of UPQC is computed as follows. The supply voltage is square wave of 230 volt RMS, and the load voltage at PCC is a sine wave of 230 volt RMS. So, therefore, series active filter must inject the difference between these two voltage to provide the required voltage at the load end, and the voltage rating of the series active power filter is, now we can say the difference of your 230 square wave minus the 230 sine wave, and taking only half cycle symmetry about 2 upon 2 pi 0 to pi, it comes 102.696 volt, and current rating of series active filter is already we calculated, that is a let us say supply current 20.531, and we can say VA rating of series active filter will be the voltage rating multiplied the current rating, and multiplying this it comes 2108.458 VA. Now, coming to another example, a single phase voltage source inverter with a quasi square waveform, AC output of 230 volt RMS at 50 hertz is feeding a critical load of 230 volt 50 hertz, single phase 5 kVA at 0.85 lagging power factor. A single phase universal active power filter conditioner or consisting of shunt and series active power filter using two voltage source converter with the common bus capacitor shown in the figure is designed for critical linear load. Calculate the voltage rating of shunt element of universal active power filter, B the current rating of shunt element of the universal active power filter, C the VA rating of the shunt element of universal active power filter, and D the voltage rating of the series active power filter of universal active power filter, and E the current rating of series element of series universal active power filter, and F is the VA rating of the series active filter, to provide the load compensation of for unity power factor at AC mains and by shunt element of universal active power filter, and constant regulated voltage sine wave of 220 volt RMS at the across the load by series element of typically of universal active power filter. So, this is the circuit that we have a like a inverter here which is giving quasi square wave and we have a this universal active power filter which have a series filter and shunt filter with common DC bus, and we have a load here, lagging power factor load. So, this is the kind of waveform, here the supply side inverter is giving it to us, and this is the supply current which is in the phase with the displacement factor unity in phase with the supply voltage and sinusoidal current, and across the load we are getting by series element the sinusoidal voltage across the load, and of course, voltage is sinusoidal, it is a linear load. So, you have a linear load current, but it has a reactive power. So, that reactive power is given by the shunt filter, and the difference of this voltage and this, typically the load voltage and this sine wave is injected by the series filter. This is the voltage across the series filter like so after making the model and with the power control with the simulation, these are the typical waveform of this circuit like So, coming to the numerical solution, given that the Vs equal to 30 volt, RMS Cauchy square wave 50 hertz, a critical load of 230 volt, 50 hertz, single phase 5 kV 0.85 power factor lagging. So, AC load current will be like your 5000, that is 5000 VA divided by 230 volt voltage across the load. So, it comes 21.739 ampere, and in this system the load reactive power compensation is to be provided by shunt active filter of universal active power filter, and voltage compensation is provided by series active filter of universal active filter. However, there is a difference in magnitude of fundamental voltage in the supply and load terminal. To compensate that, an active power is circulated between the series and shunt active power filter to, as explained in UPQCP, the rating calculation for both VSC of UPAC are as follows. So, load active power is calculated as SL into PF, that is 5000 into 0.85, so that is 4250 watt, and the active power component of load current is estimated as PL upon divided by VL, so that is 4250 by 230. So, it is 18.478 ampere, and the voltage amplitude of Cauchy square wave is estimated as typically from here 281.69 1 volt, and the fundamental voltage for Cauchy square from this relation comes like √6 by pi into VSDC, it comes 219.634 volt, and the supply current after the compensation from power and this supply voltage fundamental voltage. So, it comes 19.35 ampere fundamental current, and the voltage rating of the shunt element is equal to the load voltage of 230 volt, and current rating of shunt element is computed as the reactive power component of as the estimated reactive power of the load current. So, that is from load current under √1 minus power factor square, and putting the value it comes 11.457 ampere, and the active power component of the shunt filter which is circulated through this IS minus IL1A, putting the value it comes 0.872 ampere, and the net current of shunt active filter is active component square plus reactive component square. So, putting the value it comes 11.49 ampere, and the VA rating of the shunt active filter is the voltage of 230 multiply the current of it comes 2642.734 VA, and the voltage rating of series element is computed as the supply voltage of Cauchy square wave is 230 volt, and the load voltage at the load terminal is a sine wave of 230 volt. So, amplitude of Cauchy square wave is typically 281.693. So, therefore, series element must inject the difference between these two voltage to provide the required voltage at the load end. So, voltage rating of the series active filter is typically 2 upon 2 pi with the half wave symmetry. So, we are taking like initially when it is a Cauchy square wave, you have a 0 voltage from the inverter, but the load voltage is this much. So, that is square plus the second segment you have a DC voltage of this much of Cauchy square wave minus the sine wave square, and then again 0 voltage for 30 degree Cauchy square wave. So, this comes like a 69.052 volt, and the current rating of series element is the same as typically the supply current. So, we have a active power divided by the voltage. So, it comes 19.35 ampere, and the V rating of the series element will be your series injected voltage multiply the current of it. So, putting the value it comes 1336.161 VA. So, coming to example 3, a single phase active hybrid filter consisting of 3 branch passive shunt filter and a series active filter using a voltage source converter with the DC bus is designed for a critical load of 230 volt 50 hertz single phase thyristor with constant DC current of 20 ampere with 30 degree fire angle of its thyristor. Calculate the element value of the passive shunt filter, the voltage rating, current rating and the kV rating of both series active filter and passive shunt filter used in hybrid filter to provide the harmonics and reactive power compensation for unity power factor at AC mains like. So, this is the typical circuit. We have a supply here and we have a typically a series active filter, this is a passive shunt filter and this is the current fed off load because 20 ampere current there. So, now the role of this series active filter, we inject in a voltage that all the harmonics are forced into the passive shunt filter, and the design of passive shunt filter in such a manner that at this load the entire reactive power of the load is also provided here. So, that we have a unity power factor on the supply side. So, after developing developing the model and putting the value of the component given in the problem, we are able to have a performance simulated here. You have a supply voltage, supply current in phase with the supply current. So, unity power factor is achieved on the supply side, and this is the typically the load voltage which have a very small harmonics component just to force, and this is the load current and this is the passive shunt filter current. This passive shunt filter current consists of course the reactive power, because it is a thyristor converter with 30-degree angle firing angle. So, you have some amount of reactive power, and then it has some harmonics also, the difference of these two waveform. So, it has some harmonics also into it along with the fundamental reactive power, and you are able to see that a small series filter is supposed to inject the voltage here, to force this passive shunt filter to force this kind of current into it like now. So, after getting this waveform, we can have a numerical portion of it, given that the volt Vs equal to 230 volt, frequency is 50 hertz, a non-linear load of 230 volt 50 hertz, single phase thyristor bridge converter with constant DC current of 20 ampere at 30-degree firing angle of thyristor, and AC load RMS current is your IL equal to IDC of 20 ampere, and the fundamental current of this square wave will be your IT1 2 root 2 upon pi IL. So, it will be 18 ampere. The fundamental active power component will be your IL1 equal to IL1 cos alpha equal to 0.9 IDC, that is IL1 into cos 30, and that is 15.588 ampere. So, fundamental active power of the load will be now Vs1 into IL1 cos theta 1, and that is VL1 IL1 A. So, putting the value 230 into 15.588. So, it comes 3585.315 watt like, and the reactive power of the load will be now Vs1 into IL1 sin theta 1. So, putting sin theta 1 sin alpha and putting the all value, you will get 2070 VR is the reactive power required for load. This is required, of course, this will be provided by passive shunt filter by proper design. So, comparing that all the branches of passive filter have equal capacitor, therefore, the value of capacitor will be. So, we have a 3 element in passive shunt filter. You have a, it is a single phase, so third, fifth and high pass is the filter. So, that is the reason we have a 3 here. So, from this we are getting the how much is the capacitor we have to put for this passive shunt filter, that is the all equal. So, it means 3 capacitor for third harmonics filter, fifth harmonic filter and high pass filter all are equal, that is 41.519 microfarad, and therefore, the value of the inductor for third harmonic tuned filter, from this relation we can get the inductor 27.115 millihenry, and the resistance we get the from quality factor, considering quality factor 20, from here we are getting resistance of this third harmonic tuned filter. Similarly, value of the inductor for the fifth harmonic filter, from this tuned relation equation we get the 9.762 millihenry, and the resistance from the quality factor considering Q5 equal to 20, we are able to get here 0.767 ampere ohm, and the value of the inductor for high pass damped filter for tuned for 7th harmonic, corresponding to 7th harmonic, we get 4.98 millihenry, and the resistance in parallel with the inductor for high pass tuned filter considering the quality factor which can be between 0.5 to 5. So, we are selecting here 1, so it comes 10.952 ohm, and third harmonic load current to flow into third harmonic tuned filter is your IT1 by 3. So, it is 18 by 3 by that is 6 ampere, and the third harmonic voltage at the load end, we can have a I3 and R3. So, putting the value it comes 7.668, because the inductor drop will be completely cancelled out by the capacitive drop, only resistance will take the drop of this voltage. And similarly, we can find out fifth harmonic current to flow into the fifth harmonic tuned filter, that is I1T, that is fundamental current divided by 5 for fifth harmonic. So, it is a 3.6 ampere, and the fifth harmonic voltage across this will be your I5 R5. So, putting the value it comes 2.76 volt, and all other harmonics of load current to flow the high pass damped filter. So, from the load current we are able to let us say have a typically subtraction of RMS value of fundamental current, then third harmonic, fifth harmonic, that is the current have to go into the high pass filter. So, putting the value of all, we get the all higher order harmonics only 5.2 ampere, and all higher order harmonics voltage at the point of load end of the passive shunt filter is the current, all harmonic current multiplied the resistance. So, it comes like typically 56.95 volt, and all harmonic voltage other than fundamental voltage at the load end and across the passive shunt filter is the typically the RMS value of all harmonics, third, fifth and high pass. So, it comes 57.531 volt, and the voltage rating of the series active filter we can find out typically these harmonics voltage we have to generate by series active filter, so that much current goes into the passive filter. So, that is the series active filter voltage rating, and the current rating of series active filter is equal to the supply current already. So, we calculate the supply current, that is only active filter active power component of the load current, we calculate that is IL1 cos alpha or 0.9 IDC into cos 60, that is 15.588 ampere, and the V rating of series active filter will be voltage multiply the current. So, putting this it will come 896.812 volt ampere, and the per unit rating of series active filter if we take it as a percentage of the load. So, it comes around 19.5% of the load rating. So, that is quite much smaller rating than the typically of shunt filter, and the various rating of passive shunt filter is the voltage rating of passive shunt filter will be your typically that harmonic voltage plus your RMS. So, it is 237.086, and the current rating of passive shunt filter we already calculated total harmonics and reactive current. So, that we get from load and fundamental current which flows into the supply, this is in the load. So, difference of this it comes 12.52, and the V rating of shunt filter will be voltage multiplied the current. So, it comes like a typically 2970.67 or 2.971 kVA, that is the shunt filter rating. Series filter rating we already calculated. So, per unit rating of the passive shunt filter will be your passive shunt VA divided by load rating. So, that comes around 64.58%. So, major amount of loading goes to the passive shunt filter. I mean the series filter consists of a small only 90 to 20, but here 65% loading goes to here like I mean also. So, coming to like a fourth numerical problem, a single phase universal active power conditioner consisting of series and shunt active filters using 2 voltage source converter with common DC bus capacitor is designed for a typical load of 230 volt 50 hertz single phase thyristor bridge with a constant current of 20 ampere at 60 degree fire angle of its thyristor, and if there is a voltage fluctuation of 10% plus and 20% minus in supply voltage with the base value of 230 volt, calculate the voltage rating of the shunt element, current rating of shunt element, VA rating of the shunt element, series voltage rating of series element, and current rating of series element, and the VA rating of series element to provide the harmonic and reactive power compensation for unity power factor at AC main and constant regulated sine wave voltage of 230 volt 50 hertz across the load by series active filter. So, this is the typical circuit. So, we have a non-linear load of current fed kind of load with the thyristor converter with the RL load, high inductance. So, that current on DC side is 20 ampere, and we have a supply here. So, what we are having now typically I mean the series active this universal filter shunt provide the harmonics and reactive power, and series filter virtually is responsible to make the voltage across the load constant, because there is a like a voltage fluctuation of plus 10% minus 20%. So, after designing properly this universal active filter, I mean like we are able to get with the proper data, we are able to get like a supply voltage, then the supply current at unity power factor, and this is the load voltage which is regulated, and the load current which are not disturbing the load, and this is the passive shunt filter current which have a fundamental reactive power because of the thyristor is converted operating at 60 degree fire angle. So, difference of these two virtually you can call load current and supply current is fed into. So, it needs reactive power and harmonic current, and this is the fundamental voltage injected in series with the line, because there have been a voltage sag and swell I mean correspond to that. So, that is about after designing and making a model of this, these are the simulated waveform corresponding to that. And coming to numerical part of this, given that supply voltage of 230 volt, RMS and frequency of 50 hertz, a non-linear load of 230 volt 50 hertz single phase thyristor bridge converter with a constant current of 20 ampere at 60 degree fire angle of thyristor, and there is a voltage fluctuation of plus 10% minus 20% supply system with a base of value of 230 volt, let the x be the per unit voltage variation and Vs dash to be the voltage across the variation. So, in this system the load current, harmonics and reactive power compensation are to be provided by shunt active filter of universal active power filter, and the voltage sag swell compensation is provided by series active filter of UPAC. However, while compensating for the sag swell, an active power is circulated between series and shunt filter as explained earlier, and under the maximum voltage dip, the maximum rating of both the VSC are realized. So, various VA rating are calculated as follows. So, AC load current RMS is like a 20 ampere, and the fundamental active power component will be IL1 cos alpha. So, IL1 in case of square wave is 0.9 into, that is root 2 to divide by pi, that is 0.9 into 20 into cos alpha, that is cos 60, that is 9 ampere, and the active power consumed by the load now Vs into IL1, because it is typically is 2070 watt, and now supply voltage under the maximum voltage sag will be your 20% sag. So, it is 184. So, supply current under the maximum voltage variation minus 20 will be PL divided by lower voltage. Power, active power will be the same, I mean which is drawn from, and voltage lower. So, supply current will be 11.25 ampere, and the voltage rating of the shunt element is equal to the load voltage of, because it is connected in the shunt, that is 230 volts, since it is connected across the load of 230 volt sine wave form. So, current rating of the shunt element is computed as follows. The shunt element of universal reactive power filter is to provide the load current harmonics and reactive power compensation. Hence, required current and reactive power, harmonics current and reactive power of the load it has to supply. Therefore, total harmonics and reactive power component of the current of shunt filter is calculated as follows. IS as IL square minus the fundamental active component square. So, it comes around 17.86 ampere, and the supply voltage is lower as compared to the load voltage. Hence, the shunt FE absorb the active power, and that active power deliver back to the via series active filter. So, under voltage sag, the active power filter current is calculated here IS minus this. So, this is typically the current which have to circulate through this series. So, it comes 2.25 ampere, and the net current rating of shunt active filter is your active component current square plus reactive component square under root of that, and putting value it comes 18 ampere, and the voltage VA rating of shunt element is your voltage rating of shunt element, that is the load voltage 230 volt of sine wave, and current is 18 ampere. So, it comes 4140 VA or 4.14 VA kVA. So, voltage rating of the series element comes, there is a voltage fluctuation of 10% and minus 20% in supply system with this base value of 230 volt. So, therefore, series active filter must inject the difference of the maximum of these two voltage to provide the required load voltage. So, series voltage rating will be for 20% is the maximum sag. So, that is 230.2 is 46 volt, and the current rating of series element same as the supply current. So, that is your 11.25 ampere. So, V rating of series element is your voltage multiplied the current. So, this is voltage rating, this is current rating. So, V rating comes 517.5 VA like